All right, so what we're going to do tonight is we're going to do a crash course on the internet, the technology of the internet, and how things work, and primarily talking about the hypertext transfer protocol, and just sort of understand where the internet came and kind of understand generations of the internet, like where technology has changed and what times that has how things got to where they are today and where we're going to go. So let me. All right, so real quick, we're going to go just so we all understand a little bit of the history of the internet because a lot of people don't know much about it, I think. Um, if you get a chance one day, you should take a look at this guy, J.C. Licklider. I'll tell you a little bit about him. And basically, J.C. is the father of information theory. And we'll talk a minute about that. He came up with the idea of his vision was an intergalactic super network. And he was back in the 50s and 60s. And J.C. Licklider is like an Einstein. He's a very important person in our scientific world, but people don't know him. He's the one that figured out all of the mathematics that allow us to transmit information over networks and how to do the routing. Like theoretically, like the mathematics of how to calculate routing tables and do the math, like the low level math, like how can you digitize a photo and turn it into bits? Like it's like information theory in the sense of like how do you take information as a picture and turn it into bits? How do you send it across a wire? How do you use that wire? How does that system error correct and make it so you don't have to repeat entire blocks of messages? So that he came up with the idea of the packet, and he did all the theoretical.
Is that all part of the TCP though?
No, but he's the guy that laid the foundation for all of that with the mathematics.
Oh.
To actually discover you could do it mathematically, like that the mathematics would support the algorithms essentially to develop algorithms that could error correct and make so you could send data. So that for instance, you could be downloading a file, and the internet works through a series of routers essentially, and that's the hubs that connect all the computers, and that if one of those hubs would die and there's still a connection available to another to your destination but not through the shortest path, then how does it figure out how to get to that new destination, and how does it not have to repeat the entire message again to transmit it? Because if you ever notice, you can be downloading a file here. You could go home. You could continue to download the file. Not all files support resume, but it's possible. And the mathematics of everything that went into that, not the electronics. He wasn't an electrical engineer or anything. He was a mathematician, computer scientist. He's one of the first computer scientists. He's like the father of computer science, basically. And he developed all that. So if we didn't have JC, we wouldn't have the internet. Like we wouldn't have the network. So he's like kind of an important guy. So JC, he got into ARPANET, and we're going to talk a little bit about ARPA, which is just kind of interesting stuff. Did you guys ever hear ARPA? No. So let's talk about ARPA. So ARPA stands for the Advanced Research Projects Agency. It was founded like in 1950 something, 60.
By the military.
Well, we're going to talk about that. We're going to get real precise about this. So, and ARPANET was the first draft of the internet. Like so, ARPANET, one of their first projects was to develop the intergalactic super network that J.C. Licklider envisioned. So, they got tasked with taking the mathematics that Licklider came up with and the vision that Licklider had to actually make a packet switching network. Okay, we'll talk a little bit about what's called circuit switching and packet switching, just in brief, so we understand what that is. The impetus for this was that the Sputnik, I'll say Sputin, Sputnik, let's fix that.
Sputnik, yeah.
Yes. Sputnik was launched by the Russians, and it scared the crap out of the United States because at this point, the Russians had stolen the bomb, and they got into space first. So in Sputnik, they just put a small satellite and eventually launched a dog, and the dog. You remember they launched the poor dog, Laika, and just shot the dog up. Like, why did you do that? That's so weird. Um, anyway, that scared the crap out of the United States because essentially, up until this point, the United States really had a total power play with the atomic bomb, and the another way to look at it is wars had been fought with the same kinds of things for a long time. Men. That first they had swords, then they had guns. They've had guns for hundreds of years, and then tanks came, and tanks were kind of like an upgrade, but not a oh wow, this is gonna like a world changer. It's a bad day to have a war when you don't have a tank and somebody else has a tank, but generally tanks are not like a super weapon. So what happened was the United States got scared and they had to address this, and what happened was we got our buddy Dwight D. Eisenhower. Now, can anybody tell me, I ask this question all the time, can anybody tell me one or two things about who Dwight D. Eisenhower is?
He's Army General.
Army General? Supreme Commander of the Allied Forces of World War II. He was a president. So he was the top general of World War II for the European and Pacific theater. So he was the boss of the war on the Allied side. And after the war, if you remember, FDR died. He died in office, and then Truman took over. And then Truman didn't. I think he only had one term, and then FDR came in, and Eisenhower came in and won 2 terms, and he became president. He was the 34th president. So Eisenhower's kind of an interesting guy, and his background working with the military and working with civilian organizations gave him a unique perspective on the interaction between the military-industrial complex, the military, corporations, government, and how they ran. And he was very concerned about how things were happening in the military and in the government, and the fact that there was this new need to not just have, we needed more new super weapons. We needed more types of revolutionary technologies, not in order to stay ahead. And the first project that they did really was with ARPANET, and ARPANET was, like I said, it took J.C. Licklider's mathematics and his theories and his vision of a galactic super network, and over 10 years they worked to finally release ARPANET in 1969. Okay, so ARPANET 1969, just to understand what it consisted of, was, and this was like it wasn't quite the Manhattan Project of engineering, but it was pretty tough, because up until this point they didn't have computer chips. They didn't have
transistor? Micro
dead vacuum tubes. They just were starting to get transistors. They were just starting to get it, and that what they and what the condition was that all the computers in the country that they were going to want to hook up to this network were all made by someone in their garage. They were all handmade, homemade operating system, homemade everything. There was no standardization for any computer in the country. They were built piece by like a custom thing, every one of them. So one of the problems is that none of the computers spoke the same language, and they were all over the country. And so in order to develop this, what they had to do is they had to develop what would become a router, okay? and then they had to develop what would become the Ethernet card, essentially, which it wasn't an Ethernet card, it was an Ethernet box. Like I remember seeing it, it was like as big as this desk. Or I think it was maybe about this big, like tubes, and they would hook this up, and then like this is the, imagine this is your card that's a network card. They hook this up to that computer, and then this thing's job was to translate whatever language that, it was custom made per computer, so it could translate what that computer talked to a standardized format, which was going to eventually become the TCP/IP protocol, and that's how. And then they hooked these up to routers, and then they built ARPANET. And the things you got to kind of appreciate about this situation is we didn't know when they started. We had no idea how to electrically connect, turning a picture or turning text or anything into data that could be transferred or wired. So they had to figure that out. They had to figure out how to route the signal from and make the routers work so that if we had a nuclear bomb blow up in one place, that the whole country didn't lose communication. That was the main reason for the network. This was a lot of serious engineering. Like this is the smartest engineers in the country and the world really worked on this project. So eventually they got it to work, and Eisenhower, going back to ARPA a little bit, the reason why ARPA got created, and let me see if I got them on the next page, but I didn't have it. No. One of the things I want you to do, like, it's for fun. This isn't for, this is for kicks. You should watch this speech. I don't think it's that long. You should watch this speech because you live in America. I don't know if you're all Americans, but
I'm an American.
you're American? Everybody American?
Yes.
Or citizen or something?
I'm an Indian.
Okay, so all of our, if you're here, you should watch. Okay, so Eisenhower farewell address. We don't have time to watch it. They have videos on YouTube. Let's see, it's like 15 minutes, 20 minutes long, and yeah, it's in bad quality, but you got to watch it because the guy, you what? No, I don't have a plug. I don't have that plugged in. I'm not gonna play it.
Unmute. That's fine.
To do it the whole time.
There. No, you just had it.
And television networks, by the opportunities they have given me over the years
So
to bring me
we don't need to go through it. But it's like 15, 20 minutes long. And it's one of the most unique farewell addresses of any president ever. Like, this is like the most unique one. And the reason is because he said he goes through it where, let me go back to my presentation here. He says that basically, you know that old saying, Houston, we got a problem? And his problem that he was calling Houston about was the fact that what he saw in the military was that the military after World War II had a lot of power, a lot of money, and they were researching independently. Like you'd have the Army and the Navy. The Air, most people maybe not know that the Air Force came after World War II. So in World War II, the Air Force was part of the Army. And then after World War II, the Air Force became its own thing. The Marines became their own branch, sort of, and then you have the Navy. But up until it was just the Army and the Navy. So what was happening is the Army's researching something, and then the Navy's researching something. And so, to put it another way, the Navy is researching bullets, the Army's researching bullets, and the Army wants to get Army bullets, and the Navy wants Navy bullets. Okay? Well, they both want bullets. Okay? And what Eisenhower's saying is that a couple things, and that's what he talks about in the speech, is one, we have to protect ourselves against the military research. We have to, as a society, we have to protect the country from basically rogue research and rogue collaborations between the military-industrial complex and the military, because you don't have a civilian oversight of this. Like that relationship is sort of in a gray area of that the Army spend the money, let's say, the contractors go in, but there's no agency that's looking at like what the hell's going on. They can.
They're spending the money.
Right. What are you doing? Are you making Dr. Doom over? Is we got some crazy colonel over in in some place doing crazy experiments, or kind of like the stuff you see in the Marvel movies. So he was really concerned about that, and rightly so. And he talks about that in his speech, and he says, we have to do everything in our power to keep this under control. And so what he said was, and what he did was, while he was president, one of his big things was he said, we're going to take all the research money, most of it, I guess, away from all military organizations. Like there's like a list of certain things the military could research, like Army or Navy could look into, but most of the funding that would be for any sort of research was going to be taken away from both and given to this new agency, which was ARPA, the Advanced Research Projects Agency. And ARPA, they had a mission, or still have a mission. They became DARPA, Defense Advanced Research Projects Agency. So ARPA said what their mission was, okay, get the requirements from the military, have civilians work on the research, with partnerships with universities and industry, primarily universities. And what we're going to do is ARPA has to look at all the technologies they develop and decide what is commercializable, like what are commercializable aspects of the desires of the military. So the military could say, I want to have the internet. Like, we need a communication system that can withstand nuclear war. Okay, so that's what the military says. So ARPA goes to research on it, and then in ARPA's charter, they're supposed to take what they can when they can and transfer it over to corporations, technology transfer from the government agency to corporations to make products for the benefit of society in general. So, and that ARPA was going to be ran by civilians and had an oversight by Congress. So that's what Eisenhower did, and that's like his speech talks about why he did that, and like it's the first and only time I think a president actually just sort of like called the military-industrial complex out and told us and says hey, you're gonna have a problem. I'm leaving, but you guys gotta watch these guys because they're gonna do you wrong.
And the cat out of the bag.
Yeah, he let the cat out of the bag.
Basically.
Yeah, and nobody ever talks about this, but it's like a president went out and let the cat out of the bag on national television. So they separated it, and ARPA, the agency, eventually became DARPA, and ARPANET was launched in 1969, and the big thing was it was the first packet switch network that replaced circuit switching. Okay, so let's understand circuit and packet switching. Okay, real straightforward. Okay, circuit switching is old school telephones. Circuit switching means that there's literally an electrical circuit and a wire, and that wire is carrying a signal, an electrical signal that the amplitude of the electricity, like the power of the electricity, basically increases and decreases, and that's what transmits a voice. It's a wave. It's an analog system where it's not broken into bits and bytes or anything like that.
It's the old analog.
It's the old analog. And if you cut the wire, that's it. Okay. Just like if you cut the electrical cord on your lamp, the telephone doesn't work. And in the United States and anywhere else, they didn't have a telephone wire. They didn't have a lot of telephone wires that stretched all the way across the United States or underneath the water. Oh, they had one big cable that had a certain number of channels. That's why, in the old days, if there was something that happened in the city, the telephone switches would be blocked because there was only so many wires that you could run a telephone call through.
The operators actually handle it.
Right, they actually, you call it up, and the old school would be you called somebody up, that went to the operator, you said, who do you want to call, and then they literally plugged a plug into a switchboard, and that's what made the connection. And eventually they got to replace that with digital or some sort of switching technology that did it automatically. So that's the old school. Packet switching networks, that's what we use today. And basically, a packet is a unit of information. Okay, so basically a packet is the smallest unit of information. It's like, you ever hear of quantum, like quantum this or quantum that? Well, like a packet's sort of like a quanta. Like a quanta is the smallest unit of energy, essentially, the smallest unit of something. And a packet is the smallest unit of information. And that the packets are structured with data that is what's being transmitted and data that is going to help it get where it needs to go and make sure that when it gets there that it can be verified that it is intact and has the correct information that it has been transmitting. And so what happens is you take a picture, or you take something, or a phone call, or whatever, and it just gets transmitted or just turned into billions of packets. And those packets go over a wire. And the way they go over a wire is that the voltage, I believe, of the wire is being increased and decreased at a really high rate. Or if it's optical, it's the switching of the optical, like a fiber optics. Okay, so it's switching like that. So it's just like on and off. It's like the packets get transmitted by on and off signals. And the reason why like the routing works is because since if we have a picture and it has 1,000,000 packets and 500,000 packets go through and all of a sudden that channel, that route broke, well then the technology inside the routing system knows that there's another router, and then that other router is going to try to find a way to get to the next router and the next router, and it'll continue to transmit that information. It may go slower because the more what they call hops are the going from one router to another. So the less hops you have to go through, the faster it is. But if something's broken and you still want to get it, it'll be slow, but it'll get there as long as there's still at least one physical connection in that network of connections to get the data there. Now, I forgot one other thing. So
Fibers came after.
yeah, so I just want to call your attention to this is like just to look at the ARPA and DARPA. Basically, and I find this interesting, is that they're responsible for everything we have, like as far as technology. Like people don't realize this, but this is like people, and I'm not gonna say it, but people think that technology came from somewhere else other than the United States. It doesn't. It comes from here. Everything.
Including the chips.
Including the
And
chips.
computers. And
Everything. Like look, so DARPA, I know, look at, these are all the things that DARPA or ARPA had either direct involvement in developing or was part of a derivative that came out of their projects. So we got the internet, fiber optics, silicon computer chips, self-driving cars, reusable spaceships, Kevlar, lasers, GPS. What else would we? What other thing? I mean,
Self-driving car also they.
yeah,
No, I mean from DARPA.
yep. Because DARPA, what they do is they say they have these challenges, and like they'll say, okay, well we want to have self-driving cars. Okay, the military, like this is kind of directly how it works. The military says, hey, we want autonomous vehicles. They go to DARPA and says, DARPA, we want self-driving cars, and then they figure out how to get a bunch of money. So then DARPA gets a bunch of money to do this, and DARPA will put out $1 million bounty on autonomous, on an idea, and then they'll have competitions from researchers of any kind to get that, to do that.
grant money, right, for the university.
Well, no, the $1 million is a gift.
Oh.
That's a prize. Like, so the team that gets that money. But then that team that comes from that organization, usually a university, they get boatloads of grant money to further develop the product. So that $1 million is like paying you back for what you did to get that far,
idea.
and it's a gift to the people in the team. But then obviously those people would also be experts in what they are doing, so they're going to want to go with them to, like, so for example, I think the winner of the DARPA Grand Challenge for self-driving cars was Carnegie Mellon. And if you go to Pittsburgh today, that's where Uber's headquarters is for their self-driving cars. And all Pittsburgh not all of it, but the big thing in Pittsburgh is like the production, research, and development and dealing with self-driving cars. That's like a huge thing. Because they won the challenge, they get the money, that's where the big new technology comes from. And what, on a side, it's interesting that I find it interesting that one organization has been so responsible for so many technological developments, and they're still continuing to do this. Like they're the ones that are going to figure out they're the most advanced research organization probably in the world. And one of their new things, I got to put this in here. Let me get back to I forgot to put this in. And our new thing with DARPA, which they have other things, but this is the new big one, is brain-machine interfaces and
Prosthetic?
Yeah, just by prosthetics and exoskeletons. So, and I'll put a little thing here, Elon Musk and neural lace. Okay, so we're going to look at this in a minute. So, basically a few years ago, after the Iraq, well, I guess the Iraq war's still there, but the war on terror that never ends. A lot of people had survived horrific injuries and came back maimed and lost limbs and terrible things, okay? And it was more, because the medical technology to treat people had gotten better, more people survived with really bad persistent injuries. And so while there might not have been that many, I don't want to say diminish it, but there weren't that many people that died. There were people that died in the war. No war prior had this many people with amputations, okay? And so the main DARPA project right now is brain-machine-human interfaces to control prosthetic limbs and to develop, like, their vision is, you ever watch Star Wars and the one with Luke Skywalker gets his hand cut off and then they give him a hand and it's got, like, he opens up a pouch and you can see that it's a robot, it's a mechanical hand. So their idea is they really want to, they have two tracks right now, really. They have limb regrowth, like through stem cells and trying to literally regrow the limb. And then they also have the replace it with a mechanical limb, but not just but make a perfect copy of a hand. They want to, and they're putting billions and billions of dollars into this research to create perfect limb replacements, because they feel they owe it to the soldiers. That's the military saying, we owe this to our soldiers. We need to replace their limbs. Here's billions of dollars, and this is your priority to research. This is the next big thing. And so, in keeping with this, I'll show you how this is being commercialized at the same time. Like, where is this headed? So let's just take a look at some things here, because I just think this is interesting. So if we look at Elon Musk neural lace, this is one thing we'll show you. And this is crazy, okay? It sounds crazy. You're going to be like, like, I don't think this is happening, but it is. So the gist of it is, I was trying to find a good picture of how it works.
Got any video?
Well, let's do a video. We'll see. YouTube. Because I think a video might help, really. If I can find one that's short. So we'll go to 4-minute little. Let's do a little 4-minute.
They spray easily create flowcharts, technical diagrams, and org charts.
No one is going to watch it.
Drafting an email about the first dictative. Our brains are individuals, little gelatinous masses. But Silicon Valley superstars want to create something from science fiction that would change all that. A new tech called neural lace. Neural lace was coined by Ian Banks in a long-running set of science fiction novels. In the books, the tech helps brains interact with each other and with AI. Back in the real world, tech companies want to give your brain this same upgrade. No thank you, I say. No thank you, sir. Good day. Neural lace might sound shiny, but it's just another way of saying brain-computer interface, something scientists have experimented with for decades. This totally took off in the 90s, and by the late 2000s, there were more than 100 new peer-reviewed papers every year looking at how to hook up man to machine. We've hooked up rats to these things with mixed results. We've made it so paralyzed people could move a cursor or feel sensations. We've even made the whole system wireless. But right now, TBH, BCIs are not awesome. They suck up information about brain activity, like brain waves with EEGs, or blood flow with fMRIs. They can measure activity with electrodes, but to date, no BCI can directly interconnect and read the neurons in the brain. We just get a general idea of what's going on. And that's what neural lace is promising, a direct, hard connection. Right now, it's sort of like we're watching the brain through binoculars rather than going over and having a chat, which does make humanity sound kind of like creepers. Neural lace's promise is that the lace would be injected into the brain, embed itself, and then live there, intertwined with your brain cells, translating your thoughts into computer language, uploading and downloading information from networks, and so on. This could improve memory and allow us to keep up with AI. We could even communicate with each other. I know, it sounds amazing, but it doesn't exist. Yet, not in the way you're thinking. Yes, Elon Musk, the Lex Luthor / Tony Stark of our day, has teased it, but we're not there yet. Here's where we are. A prototype of brain-injectable technology was published in Nature Nanotechnology in 2015. After injection, this nanoscopic plastic and metal mesh embedded itself in the brains of mice. And that's it. That's it. We've invented a plug, a socket, a place where we can start to connect the brain to something else. Doesn't this seem akin to learning how wires work and then saying we've invented the internet, computer, and smartphone? Yeah, it feels that way to me too. The paper made a splash because it's the first successful embedding. Right now, BCIs require invasive brain surgery, massive computers, or they're just too crude to be useful. So this is just an injection, and that's huge. But being able to add an interface right into the brain is just a step down the path to the singularity where man and machine become one. It's just a step. Think about it. What's the neural lace going to run on? Glucose from the brain? It would need to be more efficient than the brain itself. It would need to communicate out of the head reliably, and it would need to not cause the immune system to reject it and be able to adapt if cells nearby moved or died. Right now, it's being seen as a way to deliver drugs or therapy for Parkinson's, diagnose head injuries, or treat cancers. At the moment, it's still fairly science fictional in the way you're thinking. But the promise of being completely interconnected is pretty incredible, so count on hearing about it a lot in the coming years. I mean, we're basically cyborgs already, using phones and computers to augment our brains. So why not just plug them right in? Look, we're doing all of this to better integrate man and machine so we can compete with AI, right? Well, we might be out of luck because robots can sense your emotions via radio waves. We're screwed. Check out this video here for more info. And let us know down in the comments if you are worried about AI, because
this is a couple years old.
And please subscribe for more.
And Elon.
Oh my god! I can't believe that I just did.
And the company that Elon Musk is working with is Neuralink. So
You need to have classes. You absorb the spirit.
So he got a USB port on his head. So this is coming. Like, not today, not tomorrow. 5 years from now, good chance. 10 years from now, good chance. And
Maybe soon.
it might come faster than, because you have to
Rate
imagine
of change
that
much faster.
rate of change much faster, and that there's billions of dollars being put into this for the soldier, for the
Facial
limbs.
recognition and the artificial intelligence.
So let me just finish this, and so just to show you what we're headed for is, let's see, most advanced prosthetic hand. Let's take a look. So I'm not going to play the whole video. I just want to get to the point where we see the hand.
Wrap it up, Derek. I've got a lot of shopping to do.
So now let me.
Where is this? Get something like that neural lace, what they were talking about that. And rather than having the band on the arm, just pop it in the brain and have that smooth connection between the mechanics.
Straight.
And then the exoskeleton, if you haven't seen it, it's like Boston Dynamics Exo. So this is the idea for people that are not needing prosthetics or maybe need to help with walking. And we'll just look at this real quick.
They have it for like military purposes too.
Oh yeah, this is totally what I mean. This is the military was like, oh yeah, we so you can't control the volume. They're saying their first thing was, hey, let's help the soldiers. Oh, by the way, it'd be really cool to have an exoskeleton like the Iron Man suit. So let's see here. He's gonna see if he's gonna walk. So they're building these exoskeleton suits to go around people, and like there's exoskeleton. Walk up stairs. So they've gotten,
Well, this is for the senior people.
or construction workers, or anybody who's just too lazy and has the money to. So one last little nerdy thing that has nothing to do with what we're doing, but I just want to show it to you. So this is a big thing that's coming. All right, so this guy, Joe Scott, he does these YouTube, does a lot of YouTube videos and like explains things. And long story short, I'm not gonna play the whole video, but I'll put the link in the Slack. This is interesting. So going along with all this stuff, so I didn't know this, but I didn't realize this, but did you know that a guy named, I think his name is John B. Goodenough, that's literally his name, invented the lithium ion cells? And this guy's like 90 years old and he won a Nobel Prize for inventing lithium ion. And his team of research, he's still researching, and they're going to make a next generation technology, which is called solid state batteries. Okay, and this is going to be awesome, like, because they sound fantastical. This is like, if you watch that video, he's going to say that sounds fantastical. But you got to understand that, like, the guy who's saying he's invented it is the guy that made lithium-ion batteries. So you got to take the guy who made lithium-ion batteries seriously, because he won a Nobel Prize for that. And if he's saying there's this,
Everything is lithium
it's not fake. You know what I mean? If he's got something, he's not making this up. So the new technology is actually going to, and he said it's like 3 to 5 years of commercialization until we start seeing it, is not lithium-ion batteries, but what's going to be called solid-state batteries. So batteries made like computer chips. And that they're going to be, I think it was something like 500 times more energy dense or something, and have much more charging capacity.
Keep on running for months.
They were saying like the applications are going to be that, like, you can have a Tesla run for months, like you can have an airplane out of electricity, like a totally quantum leap in what our mobile technology and what our transportation technology can be.
This is already on.
And the other thing that's going to upset some investors is that this stuff doesn't have to be made out of lithium. It's made out of sand. It's like made of silica. It's like silicon chips, but it's like, he basically figured out how to make, like, just like you print up computer chips, how to make a battery in that process. So that's going to be crazy. Anyway, so going back to the internet. So all this stuff really comes out of ARPA, or DARPA today. And if you ever were a researcher, you want to look into DARPA, because that's where all the money, that's where all the grants come out of for military research. So we get up into 1969, and then ARPANET exists, and then the public internet is released in 1991. Let me take that and move it over to here. And with this, up until this point, only universities and military installations were hooked up on ARPANET. And, you know, Al Gore, you got to give Al Gore some credit, because he did the climate change thing. Maybe people don't believe whatever, but he's putting his head out there for that. And he's also the person that got us to the internet. Okay, and what did he do? So when he was a senator, his big accomplishment as a senator was basically a bill that made the internet public. So he was the creator and sponsor of the bill that made the internet happen. So what did that mean? So in order to make the internet public, they really had to do 3 things. They had to create, one, they had to have a method for the U.S. to give away the intellectual property that they had developed for the networking, okay? Because up until this point, it was relatively secret. Now, we had networks prior to 1991, but we didn't have the kind of network that was an internet network. We had like LANs in a small office. We didn't really have WANs, and it was really expensive, and there wasn't you might have one office connected through a hard line between them, but it really wasn't a global network of any kind. And so they had to release the IP so that companies could develop the technology, the routers and the technology and everything that could support building out the internet. So that was one thing they had to do. They also had to deal with managing the internet, and they had to deal with like sort of operational aspects of making the internet run globally. And they had to do a third thing, which was they had to standardize the technologies that were going to be used on the internet so that all of the machines could communicate. So jumping down here, Tim Berners-Lee, some of you might have heard of him. Tim Berners-Lee is the person who developed the web browser, and along with that, he developed the HTTP protocol and published it in 1989. So 89 was basically when they started the bill to publicly release the internet as well. And it took 2 years to go from 89 to 91.
Mozilla?
What?
Was that the Mozilla, the first browser?
I forget what it's called. It might be.
The old Netscape, if you remember.
Let's
Netscape
just,
was the first, right?
yeah, Netscape was the first browser, but I don't know if that was directly Tim Berners-Lee's browser. His main thing was the HTTP server. Like he did the browser and HTML, and like that was his thing. But
HTTP protocol is a big protocol.
yeah, so he did a major contribution to put that in there, and that became the standard communication protocol for the internet. Because on ARPANET, they had things like Gopher and Fetch, and all these different ways of moving information around the internet that weren't very user friendly, but they didn't. It wasn't a super complicated network. It wasn't very fast, and it is what it is. But when they were going to do it publicly, yeah, they had to make it a standardized system. And so that's where Berners-Lee's web browser and his HTTP server, HTTP protocol, that's what we're going to look into. That's where he developed that, and that was his contribution. So Al Gore politically made this happen, and Berners-Lee technically made it happen to have the internet. And what we have today that you need to know about are the W3C. Okay, so you should pay attention to these. Like, you should hey, I go to these sites every once in a while just to check them out and see what their news is. And we'll talk about them and see if ICANN site's working. It wasn't working right yesterday, which is funny. There, it's working again. So, what are the W3C and ICANN? Okay, we need to know this. So, the W3C is the World Wide Web Consortium, and Tim Berners-Lee is the president of the World Wide Web Consortium. So he still, I believe, to this day. And what do? So they are responsible for browsers, basically HTTP. Anything that deals with HTTP, this is them. It's not just HTTP at this point. It's really any internet protocol for communication and the data formats like HTML that are going to be sent. And they also have a degree to deal with CSS, but they don't. And they, what's interesting is people think that they control JavaScript, and they don't. They make recommendations for JavaScript, and they do things related to JavaScript, but they don't actually control the standard of JavaScript. The standard of JavaScript is controlled by ECMA JavaScript. ECMA 262. This is JavaScript. So let me put that in my presentation real quick. So once the internet came out, now you got to understand that you got to kind of put your head in the Wayback Machine and kind of imagine what the internet looked like in 1991. So I had basically the first internet connection a kid could get. I was right on the internet and I got right off because it sucked. It was boring. I just didn't have anything. So you got to put it all. So 1991 is whenever the internet was released. Then these technologies and when it was released, the only thing that we had was HTTP. So let's just put this up here. HTTP protocol browser / web client, or HTTP client, HTTP server, and just say IE, Firefox, Google Chrome, etc. But at first it was only Netscape. And we have HTTP servers, and for a long time we had just really Apache. So we have Apache web server. So, and I'm just going to put a link on that because you got to know Apache. You don't have to know it like for the class, but I'm just saying I know what it is.
What about IAS was there too?
It was afterwards. This is the
The open
mothership.
Yeah.
This is
Apache project, right?
So this is what everybody really was using, other than ones that they had homegrown up to that point. But this is to a certain extent, I think this is the standard server on the internet today. I mean, if we look at the market share, it's like broken up between a few different web servers.
No, Apache still standard.
Oh, it's
HTTP
40% probably, 45%.
And increasing day by day.
So when it first came out, we just had a web browser. You could send pictures. You could have web pages with text, and that was it. The web pages were white, the text was black, and the web pages didn't look real good, like because they didn't have CSS. They had an HTML. The first specification.
The first HTML, but now they added other parameters and passing the.
Hold on, we're getting there. So the first HTML, if you would look at it, it had colors and blink tag and had visual styling elements to it because it needed to style something. And if you look at it, CSS didn't come out until 1996. So there was 5 years of internet with no cascading style sheets. That was rough because essentially if you had a web page and you made a change, you had to change it all the pages.
Yeah, I wrote my first JavaScript in like 1996.
So in JavaScript was developed by Netscape, and that came along in 1995. All right, and the thing to know about this is just that AT&T bought Netscape, or I think AOL bought Netscape. AOL bought Netscape and had to give away JavaScript to ECMA to maintain as an open standard. So at this point, the internet wasn't popping. The biggest development really on the internet at that point, really the earliest one, is in 1994, Ras Lerdorf. He invented PHP. And when PHP came out, that was the first time that you could really easily get data out of a database and put it on a web page. It was like the first programming language to be able to work on the internet other than Perl. And so I'll just do a little. So the internet at this point was, I call this like internet really, there was like internet 1.0. Let's break it down like this, is like ARPANET was like internet 1.0. Then we get internet 2.0, public release. Then here we get like internet 3.0, programmatic capabilities. And this sort of sets the stage for what's coming next. All right. And let me just so So here, what we have is like if you looked at the internet in the mid '90s, the web kind of sucked. We didn't have Google. We had a problem with porn, which we'll talk about in a second. Because to understand the internet, you got to understand porn. Really, like porn and the internet are like two peas in a pod.
How so?
Oh, we'll get into it. Like you'll understand in a second. Like it's real. Like, I'm not making it up to be a joke. It's really like if you want to understand the internet, you got to understand porn. It's not a joke.
Is that how it's financially backed?
Well, I'll explain. Yeah, I mean that's part of it, but it's more than that. So the internet sucked in the '90s because there was no Google. We had a big problem with porn, which I'll tell about in a second. And the reason the web sucked really are bad search, Yahoo, people didn't know or couldn't write programs with a database easily. Server-side and client-side programming were in their infancy. Web browsers were compatible with the web browser was compatible, or IE sucks. Just say this. Web browser. IE sucks and should never be forgiven. So Microsoft tried to run the internet. So they figured there was Netscape, and that was what people downloaded to get on the internet at the time. And Microsoft decided, hey, let's make our own browser, which became Internet Explorer. But hey, I know we have this W3C thing that is our international standard of specifications. Let's not obey anything of their standards, and we'll just make up our own browser and force it down people's throats. Because we own the operating system, and we're just going to install your browser for you by default, and we're going to try to force. Microsoft wanted to force the internet from being an open standard managed sort of through the W3C to being a Microsoft standard to go just IE, and the soldiers in the browser wars fought. I was a soldier in the browser war, and it sucked. I hated Microsoft. That's why I don't like Microsoft products at all, is that they would basically, you'd have to make a website for Mozilla or for Netscape or any other browser which followed standards, and then Microsoft didn't follow the standards. And one of the big ways they didn't follow the standards is like measurements. So like in browsers, you measure by pixels.
Yeah.
And Microsoft would have pixels, but what would happen is that they calculated a different. Imagine like the browser is sort of like a canvas, like a painting on a canvas. Like a normal browser has a set canvas that's like this big, and then Microsoft made their canvas a different size so that if you had measurements specified for the default normal canvas, everything got all stretched out. And it just was a nightmare because and if you look into it still to this day, in Internet Explorer, they have function. It's the only web browser in existence that has if statements built into it to have to repair poorly made web pages that have to be fixed for IE. So IE has what's called conditional if statements that if it's like, if IE, go do this. Because IE sucks. Edge is the first browser that doesn't suck. But for all the damage that they did before, I don't want to have nothing to do with them. They've done a lot of crappy things. They're doing some good things now, but they caused a lot of problems. Anyway, so in the 90s, it sucked. And then going back to the porn, what we got to understand is that
I walked in, I don't know what happened.
So there was no e-commerce, okay, at this point, because people couldn't pay for stuff online. Right? There was just information. We couldn't have e-commerce. And that was a big roadblocker. Well, turns out that a guy who ended up being friends with a guy who worked on a porno website, like he was a manager, he knew somebody and they got into it. But this guy was like kind of a bum, but he was a computer science genius, with a hacker doing it in his basement. And what he did was he came up with a way we process credit cards online. So the way our credit card system for whenever you put your credit card in to buy things online, that was invented by a guy to charge people for porn. That's how that came about. And because of that, the porn industry was the first industry that actually made money on the internet. Like it was the first input of cash. Everything else was really just companies that had been set up to provide information, and there really wasn't any real serious business model on the internet to make money, because you couldn't transfer money over the internet until this guy came up with his method of sending credit cards over the internet. So that's why like porn is part of the internet. Like it's a piece of it that has to be understood. And that, just as I put a link in here, but there's a movie called Middlemen, and the movie's about this. Like that's what the movie's about. It's like, and it's funny because this guy gets in all kinds of it's a true story. It's that, like, how did we get to have credit card processing, and what happened to this guy, and what his life was. And it's a crazy story. Like, because you should watch the movie, but the gist of it is the mafia has a lot to do with the filth industry. And when they heard about a guy who invented a way to send money over the internet securely that could pass a bank, they were all over that. And they were going to kill that guy, and they wanted to just take that. They were basically going to try to lock this guy up, and they wanted it all. Like, they didn't want him to have any credit. Like, he already had delivered the devices and the stuff that had to use for the credit cards. Because he already put it together. It was already working, and they didn't want him to go and patent it and sell it and they just wanted it to monopolize it. And so there's a whole funny story about how this all came about. It's called Middlemen. It's a great movie. And so this is all what's going on. And then, let me just see for a second here. Oops, let me just get my slide in the right spot. All right, so the big things start happening in the late 90s, okay? So these are two big deals that changed the internet. The one was Google launched in 1998, and we're going to talk a little bit more about that. And Roy Fielding, who you probably never heard of, but you should know his name from now on.
Oh, yeah.
He invented REST. So he did a doctoral dissertation, and you could kind of think of Roy Fielding as the Tim Berners-Lee 2.0.
It's the RESTful protocol, right?
Yeah, that's representational state transfer. And we're going to talk a lot about this.
APIs.
So let me see something here. So I got people like to hear about this. So we're going to take each one of these and we'll talk a little bit more about this. So this relates to Google. So the issue was that, going back to porn, is that they were the only ones that had money. Okay, imagine, like, they're the only ones that have the credit card processing, and they have lots of money, and they want to sell their product. Okay,
Invented, right?
what'd you say?
He invented, right? The guy in the middleman?
Yeah.
Oh, you haven't invited.
Oh, wait. So what happened with the internet, and people have to understand this, is that before Google, the search engines that they had were keyword counters. And some of them were examples: Excite, Hotbot, Alta Vista.
What about web crawlers?
There's web crawler.
Lycos.
Yeah, Lyco. I know all these.
I went through all references.
And so these were, let's say, example search
me on his email.
Email. I thought it
That's
was
by
web.
Microsoft.
Yeah, the web browser too.
So what happened was that because the porn industry had lots of money, they could pay for the first search engine optimization technique. And first SEO was keyword stuffing. And what happened is that you would have a page, let's call it a page of filth, and in the page they would have on white text, and it would be happy cats, mother's biscuit recipe. They'd have just random phrases in the page, and then the search engines would just count up how many times those words were repeated. And if you typed in mother's biscuits recipes, then whatever page had mother's biscuit recipe in the text, that was the top result. So with the overflowing amounts of money that was in the porn industry just took every single keyword that you could possibly type in and stuffed it into the pages of everything. So pretty much at some point, anytime you did a search on one of these old search engines, you're probably going to get porn. Because it's just you're not searching for porn, but it's been tricked into just put porn in there. So those meta tagging it, and then those search engines, they were no good. They weren't good for other reasons, but this just caused a lot of problems. And this is where Yahoo comes in. All right. So where Yahoo comes in is that, just take him out of here and put him up here. Yahoo had the directory, which doesn't exist anymore. And do you ever hear of a guy named Jerry Yang? No, nobody. I know you do. What? Yeah, Jerry Yang founded Yahoo. Okay. So where's my Jerry Yang slide? I lost my Jerry Yang slide.
No, you had it.
I just had it. Where is this?
Right there.
Oh, there you go.
Well,
So, why is Jerry Yang a moron? That's the question everyone asks. So what did Jerry Yang do? Jerry made Yahoo. And what did Yahoo do? It did one thing at the beginning. Now it's like a big hodgepodge of a bunch of things, but it did one thing. It had what's called the Yahoo directory. And the Yahoo directory, because of the search engine porn problem, instead of going to search engines, what people did was they went to Yahoo, and that's why Yahoo is the biggest, it was the number one site on the internet for years and years, because that's where you could go and like a Yellow Pages, like a phone book or something, you could look up, oh, I want to find out where my kid's school website is, or I need to know this, or I need to know, I want to see an anatomy book, or whatever, just like a directory of websites. And the difference between what Jerry did versus everybody else is Jerry had an army of people manually categorizing websites and taking ones that were submitted to them and going out and actively finding them and putting and organizing them into a directory of all of the websites that were on the internet at the time. So Jerry was like doing great because Jerry was dealing with the fact that there was the keyword stuffing problem and the search engines didn't work. So the only way you could get any decent information was to go to Yahoo. So how does he do this? Well, he goes to ICANN because ICANN, ICANN's the Internet Corporation of Assigned Names and Numbers. And they're the ones that control the IP addresses and all the hardware networking that goes on with the internet.
Is also controlled by
Yeah.
these guys?
It's the everything that runs the internet is controlled by them. So ICANN was one of the things that came out of the Al Gore thing, because they had to make a nonprofit international organization to deal with IP addresses and domain names and all of that. Anyway, so Jerry Yang, why is he a moron? Because that seems like he became a billionaire or a millionaire. I don't think he's a billionaire anymore. Why is he an idiot? Well, when Jerry and Yahoo were doing really well, the Google guys, Sergey Brin and Larry Page, lived near him, and they got a meeting with him 1997, 1998, and they went to him and said, hey Jerry, we got this search engine technology that's really good. Could you give us $5 million and you can have everything? We just want $5 million.
He is a moron.
And Jerry said, and they're like, we'll go to work for you, and and that's it. So they did this at a hibachi restaurant, and Jerry laughed and he said, I don't believe that search is the future of the internet. I believe in my directory, because he drank his own Kool-Aid. And the rest is history, because Yahoo fell apart. Yahoo is like a non-entity on the internet. Like, it's like the only original internet company that has no purpose. All it is just one big site of clickbait. So once that happened, the Google guys decided they weren't going to go get investors like that. They weren't going to sell it, and they were going to make a company, because they got pissed, and that they set up a computer under their desk at the school, and that became the first Google server, and that's when Google turned on for the first day in 1989 or something. And so when Google turned on, it rapidly started to become popular. Like, it just started, it took off really, really pretty fast, because people didn't really like the directory idea, and the internet was growing so fast that the hand collecting of websites was just not going to work. And even still, that wasn't as accurate as how well Google became with search, and that's why Google dominated. It became the dominant company that they are today. So let me move this up too. So here we're with Roy Fielding. Oh, let me see. Let's stick another slide in here. Internet 4.0 really begins with Google and Roy Fielding. So this is really sort of the epicenter of where you start to get the internet that you're familiar with today. All right, and why is that? So Google handled the search. Okay, so Google handled the finding of information. Roy Fielding figured out and described the architecture of how the internet is constructed today. So he didn't invent a protocol per se. He invented if you look at his dissertation, it's architectural styles and design of network-based software architectures. And this is how the internet works today. So what is this? What is this? So let me do this real quick here. My bad. All right, so Google handled the search. Fielding did the architecture of the internet, and with Roy Fielding's architecture design, we ended up with things like examples of new architecture. We ended up with YouTube. Well, actually, the first thing was Google Maps. Then we ended up with YouTube. We ended up with Facebook. And on and on. So Google Maps was the first real implementation of a REST of a REST application that people came in contact with all the time. So what is REST? REST stands for Representational State Transfer. Oops. And oops. And REST is basically the modern architectural design of the internet. And what does that mean? So Roy's big idea was to stop thinking about the web like Tim Berners-Lee had designed or defined, which in Lee's mind, he had a web that was just connected data, like connected web pages. It was just hyperlinks between pages, and that was the extent of what Berners-Lee had put together, because that's what the internet was just web pages connected to each other. Roy's big idea was that stop thinking about the internet as a series of web pages. Think about the internet as a series of applications and databases. Okay, database applications. And so what his art paper described was, how can you take the HTTP protocol and use it as a method to create an internet application? So how can you turn the internet into a series of networked applications instead of web pages? So today, if we fast forward here, from when he had his dissertation in 2000 and then things took off till now, the internet is no longer a bunch of web pages. The internet is essentially a web application servers that broker communication between HTTP clients and databases. All right, so what does that mean? So if you were to look at this, what you would see is this is a common architectural sort of diagram of what's happening in most modern web applications and mobile phone applications. So you have, on one side is the server, and on the other, or servers, and on the other you have the client, okay? The one server, which is the essentially static file server or HTTP server, it sends over HTML, CSS, and JavaScript to a browser, okay, then that user interface is rendered in the browser. And what it is that all of the pages whenever you're internal to the application, when you click on links, you're not going to new web pages. The program that was downloaded the first time you went to the website is generating those new web pages for you. Okay? So when you click on the link, I mean, if you go to a different site, you're going to a different site, but if you're staying inside Yahoo or Time or CNN.com or wherever, you're just, when you first went to that CNN.com, they loaded a big JavaScript program into your computer, and every time you click a link on CNN.com, all it does is it sends a message to the web service, the data service server, and it retrieves back the new data for that page, and then the JavaScript will render that data inside the new page. So you're not sending back and forth whole web pages every time you
This
click
is
on
the
links.
SPA though, right?
Yeah, this is
Single page.
a
Now
single
that's
page
the new
application.
page
I would call it new. This has been around a long time.
now. Yeah, but
Like
now,
5-6
like,
years.
Websites are actually using it as just a single page apps.
Yeah, this is most of the big websites have been replaced by this. So what we're going to look at is what's called a single page application, and I sort of put together this walkthrough of it to understand it, because the back-end developer, like what you're going to make web services, your web services that you will make in this class are for providing the data to the single page application. Okay, that's the purpose of the REST API. It's the REST API, it sends data to a client, and this is how it works. So let's say we go to njit.edu. The first thing that happens is the web server sends you one index file that contains the basic structure of the application, like just it's like a list of things to download essentially. Then with that, it'll download a compressed JavaScript file and one compressed CSS file. So once that happens, the browser runs the JavaScript file and then dynamically builds the web page you see. While the page is building, the browser makes a HTTP request to a REST server or a REST web server or API server, and that server returns the data from a database in the format of JavaScript object notation, JSON. The program in the browser then takes the JSON and renders the data in the application to show you your user profile, a list of records, or whatever is that you expect to see on that web page. And every time you click on a link on that page that is internal to the app, the browser intercepts that click and triggers a new page to be rendered based on the original JavaScript program that was downloaded the first time you went to the site. Only the data displayed on the page is changed, and this comes from another HTTP request to a REST API server. So when they say they're single page applications, the reason why they call them single page applications or SPAs is that there literally is just a single web page that is the application, and everything else is just a page, a fake page that's been rendered by the computer program that can generate web pages. So the JavaScript program that gets loaded in the first load, its job is to generate new pages or the pages for that app or that website inside the web browser, and to go and trigger when you go to one page or another to go and get the data that you need for that web page, and that data is the only thing that's sent. Now, this has some pretty big benefits for providers of SPAs, okay? Users too. So one, pages load faster because you're not loading a bunch of HTML. You're just loading the HTML the first time you went to the site, and then everything else is just these API requests to REST API, what Fielding designed, and so there's less physical data being sent over the internet, which lowers the cost of hosting sites that have millions of users. Because sites with millions of users, they don't want to send, all that HTML for every single page, for every single request. They'd rather send just the data, like just the data in the smallest format to get that page to load. This also came along whenever we started having mobile phones, or smartphones. And so with smartphones, this SPA technology really helps because now our phones today have pretty good bandwidth, but older phones, like whenever we had 3G and such, they didn't have great bandwidth, okay, and they were slow, and they really wanted to have a way to speed them up, so that was one of the things that pushed people to develop SPAs, was to reduce the amount of bandwidth that had to go to a mobile phone and make it so they just had to get the data, which was the JSON data, which we'll look at later, to it. And today, which you might not know, probably most of the apps in the app stores, in Android store or iOS store, are all actually just single-page JavaScript applications that have been packed up for distribution in the store. So they just take, the majority of the apps are just, somebody wrote a single-page application in JavaScript. They use a technology like PhoneGap or Iconic, or there's a few different types of technologies that will allow this to happen. And they just use a shell they basically put a shell around the SPA, the HTML, CSS, and JavaScript app. And then that shell allows them to put it into an app store and be installed on your phone as an app. So, because it's hard enough to get regular programmers, finding a bunch of Android programs and iOS programmers for all the apps that need to be made is really impossible. And so you find that the majority of the apps you see are some form of JavaScript app that is being embedded into a mobile phone. So if some of you might have heard of these like React or AngularJS or Vue.js, these systems are designed to make SPAs, okay? So in order to do these, you have to understand how to make a REST API, because the REST API is literally like, there's the JavaScript application, here's the REST API that sends data. If you don't have both of them, like the backend and the SPA, you can't do this. So like the reason why in this class we're not making websites, we're making backend and doing Python and backend is because in order to make it worthwhile to learn web technology today, we'd have to really have a whole class just on SPAs, and you'd already have to know everything that we were doing in this class in order to work on that, because you'd have to know how to get the data out of the server, you'd have to know everything on that side. So to do real web stuff with front end, you have to have SPAs. Everything else is worthless to know because nobody really builds web pages the way you might think. They're all just a JavaScript application, and the job of that JavaScript application is to generate pages on demand. Just dynamically create the pages inside the browser and get data from a REST API. So just to say a little bit about where the future is going, the next generation of tech is here, and this is called progressive web apps, and this will eventually replace just about all native mobile applications over the next 3 years. And I forgot one. Oops. I should say web apps and web assembly. So what is progressive apps and WebAssembly? All right, so let's just talk a little bit about this. So everybody get the idea of the SPA? We're good with that. Single page application, and it's just JavaScript, and it just generates the UI. So like I said, you'd have to know JavaScript really well to be able to work with that. So we'd have to have a JavaScript class, not an HTML CSS class. And the next generation or current generation of these single page applications is being developed by, really spearheaded by Google, but everybody's behind it, is this idea of what's called a progressive web application. So what is a progressive web application? What?
Really? So it just waits for the data when it's online. Other than that, it's still an offline app.
Yeah. So PWA capabilities. Let's see if there's a. Get you some examples here. So, what are these new apps? So why are they different than what had been before? Because you ever notice like a web app doesn't really look as good or doesn't work as good as your native phone app? Well, there's a few reasons why that is one, the browser doesn't have full access to the processor. It can't really do apps that are in the browser couldn't do what we call multi-threading and have processes to do work. And also, it couldn't, if you close down the browser, the app didn't stay alive. Okay? So these progressive web apps, they have a thing called a service worker. And a service worker in a progressive web app is basically a thread that can be used by the app to do a job. So that job could be waiting for notifications, push notifications. It could be making the UI run faster. It could be doing whatever you want. So rather than having a single threaded application that's a web app, this way you can have multiple threads and do processes on and use those multi-core processors more effectively. So the programmatic and technical speed and everything way you want to look at it of the web app now has the capabilities that a native app has by being able to use the processor more effectively. They have offline work mode, so they don't. So they install on your device like a native Android or iOS app. They're also web discoverable. So this is going to be a big change, is that as you start to see them become more popular, when you search for like Instagram app, you're not going to go to the App Store. You're just going to go and find it on Google, and then you'll go to Instagram, and they'll just install their app, and then that's what they got. Like it'll be cross-platform. It'll work on Android, iOS, same progressive web app on both platforms, and it'll work as well as the built-in native Android app. They won't be needing to install them and having updates like we do, where you update 67 things and it takes hours on your phone. That's not going to be where the
You just drop a packet.
right. It's just gonna, and when it needs to update, it'll just update in the background. They have real push notifications, so if the application's turned off, you get access to the notification API of the phone. So even if the app's off, they can still do notifications, like you get LinkedIn notifications and things like that because that works in the background. These apps can do that too. There's background synchronization capabilities to synchronize them to databases. And basically, this is the future of where apps are going to go, because it's very expensive for companies to maintain iOS and Android apps. And if they're given an option or opportunity to have a high-quality cross-platform app that's easy to install, distribute, and update, and also actually helps them to collect data better in some ways, they're going to do that because they don't want to support an Android team and an iOS team at the same time.
Why not use Xamarin or something like that, cross-platform, and just build it once and deploy it on any platform.
It's not quite as simple as that. Like Xamarin, it sort of works, but it's not quite as simple as that. And it's also, you got to get C# developers for Xamarin, and there is a very limited supply of brains to do development. Like there's not many people to do development. So companies have really decided they just want to push JavaScript because they want everybody to get into the JavaScript bandwagon and standardize on JavaScript as a technology that is
Lightweight.
it's lightweight, it does the job, and it's getting all the major money to develop and make it better. So in addition to this, the PWA, so PWAs are SPAs, they're just like super SPAs, like super single page applications. And the next thing that's happening, and this is where all the nerds are hanging out right now, like this is where I'm hanging out.
Google Hangout.
No, is what's called WebAssembly. Okay, so this is hot, and this is gonna explode. If you wanted to have a skill that you wanted to make yourself differentiated and kind of get into a little bit, this is fun and interesting and real new. So only recently, let me see when this learn more, when they dated this. I don't know when this came out, but roughly last year, WebAssembly was finally supported by all 4 browsers. So when a technology is supported by all 4 browsers, so let's just kind of lay this out. So W3C controls the browser technologies. They're the ones that research and develop and standardize browser technologies. One that already has been around, one of these new technologies that had been around a while, so that I'm going to compare a new technology that came from the W3C and how it changed the world, and how that WebAssembly is also going to change the world, and you'll be able to see this comparison. So the W3C had what's called WebRTC. Did you guys ever hear of WebRTC? No. So you need these are all buzzwords you need to know. Like if you want to talk in tech and have tech nerdy jobs, this is the buzzy words.
Tech nerd.
Yeah, this is the lingo. So what is WebRTC? So do you guys ever hear of Periscope app? What's up? Did you notice a few years ago that video cost money? Like they were trying to charge you a lot of money to have video conferences, and that kind of went away. Where now you can have Zoom and a big video conference, they do it for free. Okay. Well, this is the technology. The WebRTC is the technology that enabled that change in the business community or business models of companies, because what WebRTC is peer-to-peer real-time data transfer over the internet. So what this WebRTC technology does, and this is old. Like this didn't come out in 1989 and 2018. This was 2015. So what this does is it does network magic. And the network magic that it does is, so Sinead's there, and she wants to go make a WhatsApp call. You ever use WhatsApp? So you want to make a WhatsApp call to somebody, but they're in their house somewhere.
Okay.
Technically, there's no way while you're on this Wi-Fi network that where you're going to call can make a connection to you over an IP network, because this place is behind a firewall and they're behind a firewall, and they can't negotiate and find where your computer is here versus where that computer is there to do the connection. You understand? Well, this WebRTC protocol became standard internet technology now, and what it does is it allows peer-to-peer connections between devices and the negotiation of local area networks through the wide area network. So it's like it's easy to find over a WAN. Like the internet's a WAN, wide area network. But once you get into a building like this is the LAN. This is controlled by the routers and everything that are controlled here. This is like a black box to the internet. Well, what WebRTC does is it opens up this black box of the LAN and allows the incoming and outgoing connections to do the handshake and connect together so that you can make phone calls and you can send video and you can send files and chat messages. And
Isn't that a security hole as well?
we could talk about that in a second. And that rather than having WhatsApp pay for the bandwidth bill, like WhatsApp can't exist if they're paying for every single phone call that gets run through WhatsApp. But they don't. The reason why they don't is because they use WebRTC in order to send the data directly from you to where you're calling. So that data does not go through WhatsApp network.
It's straight over the IP.
It's straight over the IP.
Got it.
So
who
it's
does
literally
the
peer-to-peer
Yeah,
networking.
but as far as doing the negotiation, okay, she needs to reach to another peer that's over there. Somehow that peer.
So they have.
there has
So
to be
there are.
centralized
Right.
directory.
So there's these things, these special servers that were called ICE and Turn,
Mhm.
and these servers basically work as middlemen to broker the connection between the two, but they don't carry the data. They just figure out where you are, where the other person is, and then like match you and hand it off. They're like, okay, you connect, okay, we'll put you together, and then they hand you off. But the data, like that video signal that's gigabytes or megabytes per second, doesn't go through the Turn servers or any of the other network. The thing that WhatsApp's doing is basically running the Turn server to make the connection to be able to negotiate the local networks.
But they have to know when a device.
Right. So the
comes
device.
online,
So basically, what happens is when you
routers-
go and make a phone call on WhatsApp, it first goes and like Turn server. Okay. Oh, your Turn server. We know who this guy is, and then it sends a message to the person who's the recipient, and they turn on their phone or app if it's not on, and
The
then
big question is,
and
right,
go ahead.
all of these WhatsApp devices, right? I'm logged in. The Turn server and the central mechanism, it has to keep a directory of some sort.
Yes.
And at the moment you come online, it will say, okay, to get to you, this is your route. It's registered. These are the hops. This is how I'm getting.
Yeah. So like whenever you're logged into WhatsApp, you're on the Turn server.
You're on the Turn server. They know where you are. So
Right.
when somebody queries for you, it goes to that directory and say, oh, this is how you get to you. They connect those two, and that's it.
Yeah, that's what it does. But it's hot.
It is hot.
That's hot because this is peer-to-peer networking between devices versus a centralized client-server architecture, which the internet had
But
traditionally
Casa
been.
and all of those peer-to-peer file sharing. You remember?
So you can build a Casa and basically build those types of peer-to-peer file sharing services with WebRTC, and people do it. So today, any type of whenever a company, and this is like to know this because this is a business thing. Like this isn't just a technology thing. This is like a business thing. The reason why it's a business thing is because if I have a company or somebody's got an idea or we need a product or whatever, and they got to send data somehow, this is a tool that I can use to make a company that could, in a traditional client server technology. What?
Is this open source?
Yeah. So this is a totally open specification through the W3C, and all the browsers support it, every one of them. So so from a business point of view, what I'm saying is I can take an idea that wouldn't work. Like if WhatsApp came to me and said, I want to give free phone calls to everybody in the world, and they were going to do it on a client server basis, I would shut them down. They would never exist because it would be too cost prohibitive to do that. But when they were able to be one of the first on board with the WebRTC technology and perfect it, and that's why WhatsApp got the money, and that's why WhatsApp became WhatsApp. So the reason why you want to pay attention to what the hell the W3C is doing is because this is the place where entrepreneurs and billions of dollars are made. Like if you want to know what the future of the internet's going to be, the future of the internet is what the W3C says it's going to be. And these major technology developments like WebRTC and progressive web apps and the WebAssembly, which I'm going to talk to you about in a minute, this is where you can really have an opportunity to do something with technology, because in the beginning, these things aren't supported. You have like this grace period. So the grace period is money won't come until that W3C new generation technology is supported by all 4 browsers. Okay? Because if it isn't, then you get connection problems and it's confusing and it's a problem. But what you try to do, like what I did I got money out of WebRTC. That's how I went and did the VC stuff. Like my thing was WebRTC. That's why I got invested in. And how should I put this? That I got into it whenever it wasn't supported by most browsers, but kept paying attention to when it was. And that was the grace period that I had to learn it, get better at it, perfect it, and know it as a smaller technology. Let's say it more hands easily to learn because it had less development. And then it grew up, and that's how I made my business that ended up successful, because I put a video conferencing system inside of a learning management system, and that's what I sold. So like rather than have a Moodle or a Canvas that you have to get an extra video conferencing system, my system has a video conferencing system built into it. So like whenever we would have classes, it records the class, and then the class is automatically inside the LMS, and you don't have to go and add it. Anyway, so what I do, just as an idea, is periodically go to the W3C, and you want to like just look at their homepage and like, or just try to follow people that talk about it, and to keep up with what's happening here. Because if you want to be an entrepreneur, you want to have like a side hustle that you're gonna do as A, to improve your technical skills, and B, even if it's not a business, this technology is going to be in high demand for the future. Like I didn't look at this, but like there may not be tons of jobs, but they're very specific jobs. If you look up WebRTC, it's like 19 jobs, but they're all top-end jobs. And the WebRTC thing kind of like is like an interesting technology to have capabilities with. So this is also where new CSS stuff comes in, like just as an example, CSS 3D. And so like they got CSS to basically put 3D perspective on things on the page. But the big dog is this WebAssembly. So this is the, let's call this like, put in my little presentation. It's called Web 5.0. 2020s and beyond. So one, we talked about progressive web apps. But the progressive web apps also work with this technology, and it's called WebAssembly. And WebAssembly is the new internet. Like this is, okay, like let's put it this way. WebAssembly is going to let us throw away everything that we have done on the internet and do things in a completely new way. And let's just say I could add WebRTC here too. So what is WebAssembly? And the reason why it's going to get huge over the next few years is because it just had all 4 browsers take it, like built into the. So like if you get the latest version of any browser, it's got this is built into it. And what it is you know how like some of you might have had Docker Toolbox and you had a virtual machine, VirtualBox. Sounds familiar? VirtualBox. Yep. So what WebAssembly is, it's a virtual machine inside of a web browser. So you have the web browser, and then literally you boot a virtual computer into the web browser that is a directly connected computer, but with inside the web browser.
So it basically you don't even need an OS. All you need is a dumb terminal with the browser.
Yeah. As long as something runs.
Wise terminal.
And it has full access, more or less, to the resources of that computer. So the graphics card, the Bluetooth, basically it's a computer in your browser. And up until now, all JavaScript pretty much has been the only language that runs inside of a web browser. So, and that's going to continue to be to a certain extent. So, like if you took this class and you want to learn more, you got to learn like something about JavaScript. You got to know. I would say that's like the next thing you want to do. And WebAssembly requires JavaScript. But what this does is it allows you to run things like C programs, C++, I think Python. Let's see. Let me look up all the languages. WASM. There is, let me see. So I guess I can't find the list of languages, but the gist of it is, oh, here we go. So the what they call WebAssembly languages that are going to be supported in the virtual machine natively are going to be, right now it's C, C++, a language called Rust, .NET, C#, Java, and Ruby are all going to be languages that work natively inside the virtual machine. So I did a project in WebAssembly last year, which...
So this is driven by Mozilla?
It's W3C.
But it says Mozilla is driving it.
Yeah, but
The
Mozilla may be the one developing the technology, but W3C is the consortium that's like endorsing the browser control. So anybody can develop any technology, but it has to get it into the pipeline of browsers, it has to go through W3C. So to give you an example of what WebAssembly can do, I'm going to try if I can find a live demo, but also if not, they took it down. This was a good demo, but I'll just show you a video of this demo. So what we're looking at is I should have put this. This is Unreal Engine that makes Unreal, the video game system, which a lot of games are based on, running without modification inside a web browser, inside the virtual machine of the computer, inside the web browser. So, like they have, let's see, we can look at web assembly game, and where is, let's see if they have a link to it. Doom 3 online. So this is, I think this is Unreal Engine 4. And right now it's just loading up the data to run the game. And just give it a second here. So this doesn't run like a website. Because this is not a web page. This is a C++ video game with Unreal Engine running inside of the web browser. So I'll let this load and we can take a look at that in a minute. So this is like the future of the internet, where this is really going to start to come into play is virtual reality, augmented reality, because in order to use those technologies and to make them portable and easy to develop for, they are going to want to run them through browser-based technologies, and this is the browser-based technology to run everything. So, like the browser is no longer handicapped by only being able to run like JavaScript stuff. Now you can take C++ and other languages and run it in the browser. Now, going back to my little presentation here. So, where are we headed? Like when you put this together, like these three technologies, we have peer-to-peer, real-time communication. Oops. You have offline advanced web applications, and then you have native code / virtual machine in a browser with all this other stuff attached to it too. And so we're going to see an amazing explosion in like an Internet 5.0 that we're going to see over the next few years that's going to be built around these technologies to give user experiences online that have just never been possible before.
Isn't it? I think Microsoft or even Google, they're coming out.
The Stadia.
Yeah.
These are the technologies that make Stadia work.
Yeah.
Like, so Stadia is basically allowing any PC game to run through basically a browser or any device.
Any iPhone. You could have
Any iPhone, Android, everywhere. It's like your games everywhere.
Yes.
And the technologies that they're using are these to be able to deliver that. Because you don't want to have to rewrite a game for the web, but WebAssembly makes it so that you don't have to rewrite the game to make it work in JavaScript or some web thing. You can just take it and boot it up.
So kind of like a JVM.
It is. It's a virtual machine. It's a Java virtual machine, or it's a web virtual machine in the browser.
Right.
So, all right. So these are the last things we got to do, real quick. So we need some terminology here. I want you to know reading a web address. So if we look at this, we got HTTP is the hypertext transfer protocol. That's how the data gets transferred. Okay. www doesn't mean anything, but it's convention to use this if your site doesn't have a subdomain. Like so, www doesn't mean anything. NGIT is known as the domain name that you can buy, and what?
Is it available?
No. And .edu and .edu is known as a TLD or top level domain. So basically, the TLDs are controlled by ICANN. They're the ones that ICANN does domains and IPs and internet routing. Then DNS is the domain name system, and that's what ties everything together. The domain names DNS system is what converts, when you type in www.google, that's the DNS system is how it figures out how to go to a server with an IP address. Okay, and ICANN takes control of all of that. So people can run their own private DNS servers because ICANN doesn't run everyone in the world, but all the DNS servers in the world feed off of the ICANN root servers. So what we got to know about HTTP is HTTP basically, from your point of view, the main stuff that you got to be concerned with is that the HTTP message. Okay, so imagine that HTTP sends messages back and forth between the client and the server. The HTTP message has a header and an optional payload. The header, imagine that the header is what's written on outside the envelope. That's information about like where is it going, what type of request it is, what's the status of the request. It has a button, and the header is just what's on the outside of an envelope. Then you have what's called a payload, and the payload is what's inside the envelope. That's inside the message. That's the web page or data for a form being submitted or JavaScript object notation. It's whatever data is being sent in the message. So the header is like on the envelope. That tells it how to get where it's got to go and where is it going and what is it going to do. And then inside the envelope is whatever is going to be done. The next thing you got to know is that the HTTP protocol has what's known as request methods. And those methods, if you look at them, doesn't that, if you read them here, get, post, put, delete, patch, don't these seem similar to what you were looking at in databases? And so what Roy Fielding did was he defined the architecture of the network application, and he did that because he saw in the HTTP protocol that built into the protocol was all the operations needed to turn a web server into a database server, essentially. And so the way you have to think of programs, like the ones that people would write today, they're essentially the back-end program is just a middleman between the database on one side and the web client on the other. So the web application is what sits in the middle, and it is sending and receiving data from the client and then performing whatever operation the client has requested on the database server. And so you need to recognize that there's a get method that gets data. Put will replace data. That's sort of like an update it, but it replaces a whole record. Post method inserts new data. A delete will delete data or delete a record. And a patch updates data, but only the fields that, I should put that, but only updates data fields selectively. So replaces all data. So like put and patch sound a little similar, but they're not. Put will replace the whole record. Like if you had a person's, if I send a put request to a server, then I'm going to expect that it's going to completely replace the record that I'm trying to update. Okay? But if I send a patch request, the patch request will update a record, but it only updates the fields included in the patch request. So the patch request does like individual field updates, and put replaces everything. Put was originally there, but later they added patch to make it more efficient so you don't replace records all the time. So today, most of the development is done, which is developing these REST APIs, which are basically the web server or web applications that broker between the database and the web clients. So it looks something like this. So in order to develop a REST API, first you get the design of your database. You're going to load it with fake data. Then you have to make methods to do CRUD or BREAD. So these are acronyms and things, slang that people say, and you should know what it is. CRUD stands for create, retrieve, update, and delete. So those are the 4 database operations: create a record, retrieve a record, update, and delete a record. BREAD is something people are saying now more than, or maybe not more than CRUD, but this is kind of like the newer term. So BREAD means browse, read, edit, add, and delete. So browse being provide an index view, like a listing of records, because you usually see a table of records. Then retrieve is getting one record, so that's one record. Then edit is edit a record, A is add a record, and D is delete a record. So bread. So for example, if I told you to go make me a bread service, I don't want you to cook me bread. What I want you to do is make me a REST API that has the ability to browse, retrieve, edit, add, and delete records in the database through a web client. Now, in addition to the API request methods, there are API responses. Okay, these also go through HTTP messages with a header and payloads, depending on what kind it is. And there are a bunch of statuses, but generally the default status for OK is 200. 201 says, hey, this database on the web just created a record. 404 means document not found. You've seen 404s, but like in a SPA, single page application, what'll happen is I return back a 404 error, and then the JavaScript application sees that it had an error and it didn't get any data, so it just dynamically puts in a page that shows you no records. 500 is server fault, i.e. your program doesn't work. So if you see 500 errors, that's a server fault. There's some problem with it. There are a lot of HTTP status codes, and this goes through them all. And generally, to be good at making REST APIs, you have to know all the status codes, because most of the APIs that get designed, you have to handle these status codes as part of the application. It's like you're making an API to access a database, And then these are all, when you're responding to a request, these status codes tell the program that you're sending data to what happened to that request. Is it good, or it's whatever happened to it? It's the error codes that could diagnose what the problem is, and that app takes action on that. Now, last couple things. You need to look into SSL, and basically, just so you know, you usually buy SSL certificates, but you can actually self-generate SSL certificates, and they're the same thing. The only difference between a self-created on your own SSL certificate, SSL is what makes HTTPS happen. And it's what encrypts the data being transmitted between the client and server. And SSL certificates, when you buy them, let's say from something like GoDaddy, if we buy GoDaddy certificate, we look at like GoDaddy SSL, and then they'll sell them to you. But what are they actually selling you, since you can generate it your own and it's just a digital piece of paper essentially? What they're selling you is the fact that if I go to this little lock, that it'll tell me who issued the certificate, and then that certificate issuer will know who I am. So in order to get an SSL certificate, I got to provide usually at least a basic information: name, address, street address, phone number. Like I was signing up for basically
the security or the validity.
So the difference is in the cost of the SSL certificates. They're all the same thing. It's just the higher level of identity verification that took place to get it. So there'll be like different levels of SSL certificates. They're all the same certificate. It's just that company marketing that in order to get our premium certificate, and it costs you $500, they're going to make you have a Dun & Bradstreet number. They're going to make you have a Social Security number. They're going to make you have a bunch of information. They're going to talk to you on the phone. They're going to see that you're a real business to get certain types of certificates. And that depending on what type of certificate you have, the browser address bars will change color. Some of them are fatter and green, if you ever notice, and some of them are smaller, and they just change because the different levels of security verification will cause the browser to identify better certificates over less trustworthy certificates. Now, the other thing is that a big thing about security, that a word you need to know, is called CORS. This is like your first web security thing to know about with web APIs. So it's like Security 101. CORS stands for Cross-Origin Resource Sharing. So there's a security feature built into browsers that, remember how I was saying about how SPAs and APIs, they make requests back and forth to send the data? Well, what CORS says is that when a web page, like whenever that single page is sent, that page can only make requests back to the same domain that it was sent from. So if I get something from NGIT, my browser can only make requests to get data from somewhere that is NGIT. So it's cross-origin resource sharing. So CORS prevents or enables, depending on how you look at it, getting data from websites that are not where the data originally came from. So if I have, for example, a CORS-enabled application or a server, that means that, for example, someone could load NGIT, and then if I have a CORS server and I'm Facebook.com, which is a CORS server, my browser will let me make a request, and they'll accept a request in Facebook to get Facebook data out because they've hardened their server and turned on the CORS option, and they're willing to do the extra security to allow requests from
That's
anything.
Actually a gaping hole. Now you're allowing multi-sources, and you don't know where the
Right. So that's why. So that's why
Credibility.
CORS is to be enabled carefully on. it's to be enabled carefully, and you can't expect cores to be enabled for wherever you go. Like, because most of the time they only want to have it from the where it came from, the back and forth, and that doesn't need as much security. But if you're running an application over here like Facebook and you're taking requests from anything, that requires a new level of security, because that opens you up to robots hacking at you and all sorts of nasty security problems that you can get into. Because if you have cores enabled and it can only take from the browser, then that means that basically somebody has to have downloaded something from you in order to make a request back to you. So there's some security that you could shut somebody off from downloading from you if you wanted to not let them access it. But with cores enabled, Facebook has to worry about people using anything to make requests to it and hack into it. So they have to run a much tighter security ship in order to have cores enabled. So cores is just something you want to know what it is. Now, what we have here is just let's see, we're almost done. So what we have today is referred to as an SOA, service-oriented architecture. Okay? And with this service-oriented architecture, it really has two different things. One is called REST and JSON. So REST is representational state transfer. That's Roy Fielding. Then you also have, on the other side of the house, you have SOAP. Okay, SOAP is Simple Object Access Protocol. And they're very different, but both of their jobs is to enable networked applications. On the web, you're going to find REST and JSON, and in corporate backends, you're going to find SOAP.
No, JSON's there.
JSON is, but you're going to. There's a lot of SOAP going on in corporations.
Well, JSON is actually the data medium.
It's the message format.
It's a format.
Right.
The SOAP is actually a protocol, which
Right.
is XML over HTTP requests, and that's how you're going to do or you could have a SOAP.
So let me just finish real quick.
Okay.
So, like, generally, let's just say the internet is where REST comes into play, because you got to have a web server and all that. And SOAP is its own thing. It has its own protocol, its own server, its own application, and you find that mostly in corporate backends. You don't find it on the internet. There are SOAP servers on the internet, but they're few and far between, and they don't use them that much. Okay, the big difference between these two, in a way, is, and there's a bunch of stuff, but REST is basically a concept and an agreement of how we want to work together. And this is a technology that actually, like he said, is a protocol and has things like, if you do SOAP, there's a thing called a WSDL, and there's the WSDL file. I just take and make a new object with the WSDL file out of a SOAP client, and then my SOAP client is completely configured to insert, update, delete records, and connect to that SOAP service, versus where REST, I have to code a client for it, basically. So, like, some places will give you an SDK, like Facebook has an SDK for their services, but all it is just HTTP requests already pre-coded for you, wrapped up in a class. But SOAP just generates the class to be custom for it.
Contract, right? That WSDL.
The WSDL is the contract of what that service can do.
Parameters that you pass. You have to be explicit.
So what you find in businesses today, either as they already have it or they're moving to it, is that they're building this web service, this service-oriented architecture that uses these technologies to enable it. Okay, so service-oriented architecture, big buzzword.
I mean, it's been around.
It's been around. Like, let's put it this way: if you haven't heard service-oriented architecture, it's been around a long time. You might want to know what that is. So now, JSON. The big thing about JSON is that it stands for JavaScript Object Notation, and with JSON, the reason why we use JSON is that it directly turns into JavaScript. So JSON is JavaScript, and when I send JSON from my API server, like my API server could be written in C#, but if it sends JSON over, it goes directly into the memory of the browser as an object. It doesn't have to be parsed. It doesn't have to be. It just pops into as an object. It's magic. But with XML, XML has to be read, and it's slow, and it sucks. XML's slow, and the browser doesn't really support it. So nobody uses XML on the internet much.
IE did though.
IE tried to, but not really successfully. So JSON wins on the web. Corporate back offices, they do use JSON and they use XML.
No, purely like 90% of our stuff is all purely JSON. It's all microservices now. Not even it's just purely
Okay,
microservices.
so with microservices, this is like the state of the art where you're at right now. Most contracts, like you might find for jobs or activities in this area, is going to be either maintaining or transitioning from what's called a monolithic application to a microservice-based application. In this class, you learn Docker, you learn Python. Those are the two big skills that you need to know in order to do microservices, and your final project is going to be to make a microservice, or microservice is. So what is a microservice? So first, you have monolithic applications, and they do a lot of things. Microservices do one thing and live in one Docker container. A complete application is an assembly of Docker containers all running one in small programs that do one thing. Okay, so your project will look something like this. You'll have one application or one service that provides that takes a data point as an input and then provides the z-score of the data point. And that would be one complete application. Okay? Then you would have another one, which would be a service that generates aggregate statistics on the data set. And then you might have another service that displays the application logs. So a monolithic application would do all three of these things inside of that app. In a microservice, there'll be three Docker containers. One Docker container runs one app, and that does the z-score. Another app does the aggregate statistics. Another app does the log reading. And that the way these get put together is you'll see that app architecture is that the z-score app will run on port 8001. The aggregate app will run on port 8002, and then the log app will run on port 8003. then what happens is that, I'll just say Docker outside external, let's just say internal Docker containers, then external access through the Docker manager will go to a proxy server that, and its job is to take, take port 80 requests for URLs and send them to the correct micro service. Come on, like this is like too small. Yeah, we're done. But the gist of it is, when we come in next week, and I'm going to post this up and some tutorials, and you at least have to have, I'm going to put 2 tutorials and at least have one of them done by next week, because you're going to have to start making a web server, like dealing with web server, okay? And the gist of it, the idea is, Docker's run, you know, the Docker manager, it's going to run a new program, and it's going to be a proxy. And what that does is, when requests come in on port 80, it rewrites them so that they go to the correct microservice. So like, if I'm going to my service / zscore, then the proxy takes my service / zscore and sends it to port 8001. And then my service aggregate 8002, 8003. And then the end user doesn't see those port numbers. The end user is getting their data over on port 80, and it looks like it's one monolithic application, but it's actually broken into 3 separate applications that are self-contained.
Are we going to have separate containers for those zscore and that? Or
Yeah, each microservice sits in its own container. So like, what you're going to end up with is essentially probably multiple repositories for each individual app, and then another repository that's going to bring them all together to deploy them.
When are you going to post the tutorials?
I'm going to do it tonight.
You missed your train already. Why you
By the way, just so you know, this project, I expect it to be 35, 40 hours worth of work. Yeah, you're going to have a lot of fun
as
with
a
this.
total, or
Yeah.
individually, or as a team?
Probably individually.
So
Because
120.
it depends on depends on the cut of the jib of the team member, how much they know already, and how much they programmed already. But that's sort of the thing, like, because they're microservices, everybody in the team gets to make their own microservice.
That's right. Wow.
Yeah, that's right.
I'll make mine too.
As long as we have the tutorial and the right, sort of direction.
Yeah, there's tutorials that exactly show what to do. Like this is like popular being done now. So there's lots of tutorials on how to make Docker, Python, and what you're doing.
As long as we have that direction, I guess we should be fine.
And we're gonna do some of it next week.
In the class?
Yeah.
Oh, God. I just found it was on the street.